Okay, so the last time we start discussing about the magnetism, right? So if you can remember, we discussed about these things, right? So what are the magnetic materials? Means the ones they can be made into magnets, and also they are the ones which will be attracted by a magnet as well. So then we discussed soft magnetic materials means easily magnetized, and the magnetism will not remain there forever. It is temporary, and the hard magnetic materials they will the magnetism will be remaining for some time. So then soft magnetic materials example is iron, and for the hard magnetic materials we discuss it's the steel. So then we discuss the magnetic field means a region of space where magnetism can be detected. Right? So that means the region in space where a magnet can affect the other materials. And the magnetic field lines we discussed, they can be drawn using magnetic field lines. So then to identify the magnetic field line patterns, we discussed two methods. One is with iron powder or the iron fillings. So then second one with a compass, right? So I showed you how to do these things with the video, right? So then just go through the recording if you need any clarifications, right? So then we drew the basic shapes of magnetic field lines around a bar magnet and around like poles and dislike poles. And we discuss about the magnetic field lines, uniform magnetic field lines, when you have the magnetic field lines parallel to each other with similar gaps, right? And then we discussed about the induced magnetism. That means the magnetism will be introduced if you keep an iron nail attached to a magnet, so then the nail also becoming a magnet, so that one is called induced magnetism. So then we discuss the electromagnetism. That means basically whenever there is a current carrying conductor wire, so there is a magnetic field around it. I showed you the direction of it as well. So then the magnetic field lines, the direction we can identify using this right hand grip rule, right? So then around the straight wire it will be like that. And remember we drew these things right on the top view as well, right? So if it is going into the plane, we draw with a cross, and the circles we can draw around it. And I told you we have draw circles with the gap increasing like this. So then this is the magnetic field lines pattern, right? So if you draw it coming out of it, then the direction of the lines will be the opposite, right? So this is what we discussed last, I think, field lines around the current carrying loop and the field lines around the solenoid. And also we discussed the sense of the solenoid, magnetic field in a solenoid can be increased. How can we increase that? That one also we have discussed. So increase in the current, increase in the number of turns, or making into a solenoid just like that. Okay. So then what we have discussed is electric motors. So I will come back to this one later. I will skip this one for now. And I'm going to start discussing about electromagnetic induction, right? Now if I go to the board there, electromagnetic induction, check the spellings, yeah, right. Again, give me a minute. I want to show you a small video. Right, small video. This one I think is much more clearer. There's a coil, current carrying coil is there, right? So then let's say it's connected to a galvanometer. So a galvanometer means like a galvanometer means like a ammeter, okay? Right. Just observe. Right. Now see, when you bring a magnet, let me see if I can turn off that subtitles. Right, okay. Now see, when you bring a magnet towards this coil, see what happens. check this galvanometer. Can you see? When you bring the magnet in or out of this coil, you can see the galvanometer is moving. Right? So that means there will be a current in the coil. Galvanometer means like a meter, right? So it will show us a current, right? Right, so I think you will see if you just type the word electromagnetic induction in YouTube, you will see a lot of videos related to similar kind of videos will be there, right? And this is again another thing, quite similar one. Not this one, like this one. Okay. You can see this is a coil, and here is again a micrometer. So then only the micro range currents can be measured using this micrometer. And see when the magnet is moved towards or away from it, what will happen, right? Again similar thing is happening. Right. See, there will be a current. And just observe this one also, right? Now when the magnet is moved towards, when the magnet is moved towards this coil, what will happen is, right, this point in the ammeter will move towards one side, right? And when the magnet is removed, the pointer will be moving away on the other side, right? Now you see, when the magnet is moved towards, the pointer goes left, and when the magnet is removed, the pointer goes right. Right, I think that's clear, right? I think there were more examples here also there, right? Now this is a digital ammeter, right? So it shows us there's a current when the magnet is moved towards or away from the coil, right? I think that's enough. Right, so that is what meant by electromagnetic induction. Okay, so electromagnetic induction means so simply electromagnetic induction means, right, remember, whenever there is a magnet and a coil, right, so there is a current carrying coil connected like this, going through a ammeter, some sort of ammeter, and if we bring a magnet towards or away from it, you will see there will be a current in this coil, right? So similar thing can be observed if you have a north pole and a south pole like this, right? So if you have some sort of a coil like that, so connected through ammeter, right? So if you move this coil up or down, right, so then there will be a current in this wire, right? Now here what is actually happening is like this. Now when we know, if you have, now let's try to do kind of like a 3D view. Say this is north pole, this is the south pole, right? So you know magnetic field lines are going from north to south like this, right? So magnetic field lines are going like that. So then if you can move a conducting wire, right? Now this one is connected through a ammeter, right? So if we move this wire in a way that it cuts the field line, right? Now that term is important, right? So if this wire, the AB, if AB cuts the magnetic field lines, right, so what will happen is there will be a voltage induced. So there will be a voltage induced in the region. Now this is the within this section, the one I marked with the cross, that is the section which will be cut in the magnetic field lines. So when the magnetic field lines are cut by the wire, right, there will be a voltage induced. So that means when it's cut in the field lines, this part of this AB wire, it is acting like a kind of like a battery. So then voltage is induced. So because of the voltage, what will happen? Voltage means a potential difference, right? So then what will happen? Electron starts to flow across this wire, right? So that means the voltage is causing a current, right? So induced means actually generated, right? So then that means a current will be generated. Is it clear? So we have this up. Is it clear? Right. So then that is the case, right? So then same thing happens in this coil as well, right? So we know there will be magnetic field lines around this coil, right? So we know the magnetic field lines are starting from North Pole and going towards the South Pole like this. Okay, so north to south. So when the magnet is moved towards away, right? So what will happen is there will be a current generated in this coil, right? So because when the magnet is moved towards this direction, right? So what will happen? These turns in this coil will be cut in the magnetic field lines. So when the field lines are cut by the magnetic field lines, there will be a current generated in the voltage is generated, voltage is induced across this coil. That voltage is causing the current to be transferred in this coil, right? Now remember, this cutting the field lines is important. Actually there what is actually happening is the magnetic field strength, magnetic field is changing, right? So when the magnetic field lines are cut by this wire or the whatever the conductor or the coil, right? So what is happening is whatever the magnetic field associated with the coil is changing. So when the magnetic field is changing in that conductor, there will be a voltage induced, right? So that voltage is what causing the current to flow, right? So I think you have these notes, right? These are, I think I shared you before, right? Right. So then if you read this one, so when a wire cuts the field, magnetic field, right? So then that word is important. If you want, you can underline that one. When a wire cuts the magnetic fields of a magnet, the voltage is induced in the wire. This phenomenon is called electromagnetic induction. We can also generate a voltage current by pushing a magnet into a coil, right? So that's what we just explained, right? Now simply what is required is the magnetic field should be changing in the wire. So then it can be done by either moving the coil or either moving the wire, right? So in this figure you can see, so I have showed the movement of the wire. If the wire is moved upwards, so then if it is moving up and down like that, so then it will be cut in the field line. Now the thing is, if you move it horizontally like this, right? So if you move this wire, if you move this wire AB, right, horizontally, so then what will happen? The coil will not cut the field lines. It is not cutting the field lines. What happens? It's just touching, just slightly, just touching the field lines, but not cutting across the lines. So in that kind of situation, no induction will happen, right? No current will be, no voltage is induced in this situation. Okay, so it's always in a direction where the wire cuts the field lines, only will be creating a current, right? Right. Now the size of the induced voltage can be increased by several things, right? So one thing is, right, now remember, one first thing we can do is, right, so we can move the coil fast, move the wire or the coil faster, right? So another way we can do is we can use a stronger magnet, right? So then third one, I will explain what is happening here, right? So third one is use a coil, means like a solenoid, instead of just a normal straight wire, right? Now remember, so then this one is remember, sorry, I didn't share this one, no? Yeah. So the first one is moving the coil faster using a stronger magnet or using a coil. Okay. Eliana, do you have this note with you? Okay. I was saying before, right? So if the wire is moved horizontally, it is just touching the field lines. It is not crossing. It's not cutting out the line. So then it will be, there will be no voltage induced, right? Right. Okay. Now here actually what is happening is, right? So I told you even in the before, so right. So then how much voltage is induced, right? It depends on how much magnetic field is changing, right? Now if you move the coil faster, what will happen? It will cut more field lines, right? So every time what's happening is cutting more field lines, right? So if you have the field lines, let's say it's magnetic field lines are like this. So if you move the coil slower, what will happen? Within a short time, the magnetic field lines cut by the wire will be less. If you move faster, within the same time, it will cut more field lines. So if you use a stronger magnet, what will happen is, when the field is stronger, the magnetic field lines will be much closer. So that means even if it is move in the same speed, right? So in the first situation, now this is the second one, right? In the first one, the field lines are separated. That is because the magnetic field is weaker compared to the second one. So then when the wire is moving, so then it will cut only few lines. But since there are more lines in the second situation, when the wire is moving, it will cut more field lines. When it cuts more field lines, there will be more voltage, right? So using a coil, right, rather than using just a straight wire like this, if you use a coil like this, all parts of these points, that means each turn will be cut in the field line. So if it is moving the wire, if it is just the straight wire, only this part is cut in the field lines. But if you made it into a coil, so then each turn, right, so this part, everywhere will be cut in the field lines at the same time, almost at the same time. So there will be more voltage induced because of that, right? Okay. So I hope it is clear. I simply, that means whenever, just keep this in mind, right? Whenever a wire or a conductor cuts the magnetic field lines, there will be a voltage induced. Now this thing they ask, when the wire is moved like this, why there will be a current in the ammeter, why there is a reading on the ammeter. So then you can simply mention, so when the wire cuts the magnetic field lines, there will be a voltage induced across the wire. Because of this voltage, there will be a current, right? I will give you a question to write this one later, right? Right. Okay, so this is the idea of, actually now you can understand, right? When this thing happen, there will be a current introduced in this wire, right? Now this is the way actually we generate the electricity in power stations as well, right? Now before maybe moving on to the power station, we have this small thing, bicycle dynamo, right? Now I don't know if you have seen this or no. Have you seen this one, bicycle dynamo? Right. So it's a device like this, right? So if you want, now this is normally used in bicycles, not motorbikes or anything. What will happen is, in the night, right, when we need the light to travel, right, we make sure this bottle like thingy, right, you can see in the figure, right? So there's a small bottle shaped thing. see. Okay, you can see it from this figure much clearer. Right. So this bottle, the lid of this bottle, this is not a bottle actually, right? So the bottle like thingy is touch. We can move this one, right? So in the night, what we can do is we can make sure this lid like thing touches the tire. So then when the tire rotates, this top part also is starting to rotate, right? So then you will see a light turns on, right? The light bulb connected to this dynamo starts to produce light, right? So here what is happening is, right, if you check the note again, right, so here what is happening is, now this is that lid like thingy, right? Now this entire thing is like that bottle like thing is the cross section is like this, right? So here what we have is, so when the bicycle the wheel starts to rotate, this lid is also starting to rotate. So when that rotate, what will happen is, now you can see the lid, this thing is connected to a magnet, so then the magnet is also starting to rotate, right? So when the magnet is rotating, now you can say there's a coil here, right? So we know that when the magnet rotates, the magnetic field lines also rotates with that. So when the magnetic field lines are rotating, so then these two coils starts to cut those magnetic field lines. So as a result, what will happen, there will be a voltage induced in this, so which will produce a current. So when you connect this wires into a bulb, so then that current is enough to turn on a light. And you can, if you have seen this one, or if you have used this one, right, so if you start to ride faster, if that means if the wheel is rotating faster, so then it will produce more brighter light. Why is that? Because when this one rotates much faster, what will happen is, it's like just like what we were discussing here, move the wire or the coil faster, right? So then here what we are doing is, we are moving the magnet faster, so then it will cut more field lines. These two coils can cut more field lines, which will produce more current, more voltage and more current, giving us more brighter light. So then here it's explained, I think, a small generator or a dynamo is used to generate electricity for a bicycle light. As the cyclist pedals, the wheel rotates and makes a small magnet within the dynamo turn around. As this magnet turns, its magnetic field turns as well. So then the field lines cut through the coil, inducing a current in it, right? So actually here it should be inducing a voltage in it, right? So voltage is the one causing the current. This current can be used to work the cyclist's light. Is it understood?
YouTube channel. In this video, we will electrical energy in the form of an
At first, I think it's mentioning about.
So when we have relative motion between a coil and a magnetic field, an electric current or electromotive force,
this is what we just explained about electromagnetic induction,
is induced in the coil. Let's look at the basic.
Right. Now this is the basic structure inside the electrical dynamo. Now in power plants, whether in Sri Lanka or wherever the country, whatever the country is, the electricity is generated by the current we are getting in our houses. That electrical current is generated using a dynamo, right? So the dynamo means the one we are rotating, right? So that one is rotating using hydropower or steam, or any different methods are using to rotate that one. That dynamo is actually connected to a generator like that, right? So then generator, inside of the generator, it looks like this, right? So this part we never get to see inside the power plant, but this is how it is created, right? Now you can see there are, now these are not small as this, right? The ones they use in the power plants, they are somewhat larger ones. There are large magnets and there are coils, right? So here it's shown with just one coil. So then there will be, most of the time in power plants, there will be more than one coil will be rotating, right? Okay. Now here you can see a coil is there, right? So it is inside a magnetic field, right? So this The rings like things we will discuss them later, right? It will be explained in the video as well, but I will also explain while we watch in the video, right? And let's see how it is, what is
basic components of AC generator.
again. This, there will be some names, you don't have to worry much about these names, only think about the words given in your textbook. I mean, in the note I have given the figure, right? So this figure is given in the note. It's the same thing taken from the textbook.
Armature is part of an AC generator which carries a current and consists of many coils of wire. Armature converts electrical power to mechanical power.
Armature means simply the coil, okay? Just skip this part. Right, this name is important, slip rings, right? This name is important.
Of a circular conducting material that is connected to the armature rotor windings. Slip rings are used to bridge, transfer, and carry the power to and from the rotor of an AC generator. Brushes B1 and B2 are usually made of.
Those brushes are also important. Sometimes we call them as carbon brushes. You can see it is mentioned as brushes in your note as well. Brushes or carbon brushes, either it's fine.
Carbon. One end of each brush is in contact with rotating slip ring and the other end is connected to the other circuit. Galvanometer is connected to outer.
Now in power plants we don't have just a galvanometer, so this is just these wires are going to whatever the circuits we are taking the currents out of it, right? But simply this is just a demonstration, right? So normally, so whatever the device we want the current to be connected, we want to supply the current, we can connect it to this here, right? Now here in the animation they are using a galvanometer to show how the current is changing
the circuit. Purpose of galvanometer is to show the flow of current in the external circuit. Furthermore, we will explain the working principle of the AC generator. When the armature rotates between the poles of magnetic field, armature cuts the lines of magnetic field and generates current in the coil of armature.
Right. Now you can see as it rotates, this side AB,
this induced current then flows.
Right, so AB and CD sides always cut in the field lines, right? So then, but this side AD and BC are not cut in the field lines. You can see they are just moving like parallel to the field, right? So as a result, what will happen as this one rotates, so there will be a current induced in this AB and CD sides, right? Now actually they will be but there will be no current introduced in this AD and BC sides.
Flows through the circuits connected to the armature. In fact, it flows through the armature, slip rings, brushes, and through galvanometer, in which we have a response. As you can see, galvanometer needle swings between negative and positive values. This means that alternating current passes through galvanometer. Induced in the armature, it's necessary to know the direction of that induced current. So initially, armature coil ABCD is in the vertical position. Armature part AB is up while part CD is down, as you already know direction of the magnetic field is from north to south pole.
And remember, again, you don't have to know much about this much of details, right? So just go through the video, so then you will understand it better than the ones we need in our lesson, right? So I will explain again this one with the board and everything, but just go through it.
Undergo half rotation in clockwise direction, part of armature AB goes down while part CD goes up. According to Fleming's right-hand rule, the thumb indicates.
Okay, this one you don't have to worry, the Fleming's right-hand rule thing.
It's the direct course both to and from brush B1 to current will flow in direction DCBA of armature, and from brush B1 to brush B2 through galvanometer. If we take another half rotation, part of armature AB moves up while part CD moves down, again according to Fleming's right-hand rule. in fact, direction of magnetic current. In our case, current will flow in direction ABCD of armature and from brush B2 to brush B1 through galvanometer. To conclude, induced current changes direction for every half rotation. Next thing we need to see is how induced EMF changes over time.
Induced EMF means the induced voltage, okay?
To see this graphically representation of induced EMF, we have to assume that armature needs t seconds to complete full rotation. In time, t equals...
Now in this case actually, right, when at this particular moment, right, so as it rotates, it's trying to go horizontally, but it's going in the circular path. So at this point, right, so at the highest point, on side AB, it's for this particular moment only, it is moving parallel to the field line. So then at this point, that means when the side AB and CD moving in this situation, that means the plane of this entire coil, when it is perpendicular to the field lines, there will be no current or no voltage generated, right? Then see how it is changes.
0 seconds armature, ABCD is in a vertical position. Part of armature AB is up and part CD is down. Part of armature AB and part CD moves parallel to the magnetic field at that moment. Also at that moment, the rate of change of magnetic flux is 0, therefore induced EMF is...
And magnetic flux means the magnetic field.
0. For the first quarter rotation, from t equals 0 seconds to t over 4 seconds, part of armature AB moves down and part CD moves up. In this period, induced EMF increases from 0 to maximum value. In t over 4 seconds, armature is in horizontal position in relation to the magnetic field. In t over 4 seconds, rate of change of magnetic flux momentarily gain maximum value. Therefore, the induced EMF at this position is maximum. During second quarter of rotation, from t over 4 seconds to t over 2 seconds, part of armature AB moves again down and part CD moves up. In this period, induced EMF decreased from its maximum value to 0. In t over 2 seconds, armature again is in vertical position. Part of armature AB is down and part CD is up. Part of armature AB and part CD moves parallel to the magnetic field at that moment. Also at that moment, the rate of change of magnetic flux is 0. Therefore, induced EMF is 0. During the third quarter of rotation, from t over 2 seconds to 3t over 4 seconds, part of armature AB goes up and part CD moves down. In this period, induced EMF increases from 0 to maximum value, but in this period, induced EMF has opposite polarity. In 3t over 4 seconds, rate of change of magnetic flux momentarily gain maximum value, but compared to a position in t over 4 seconds, induced EMF gain its negative value. Finally, during the last quarter of rotation, from 3t over 4 seconds to t seconds, part of armature AB goes up, part CD moves down. In this period, induced EMF decreases from its maximum negative value to 0. In time...
Right. So I think it's too much details are there, right? So we don't have to worry much about it, right?
T seconds armature field is some AC or alternating current, generally refers to a time-varying waveform or sinusoid, and we saw
the current or the direction of the voltage is changing. So this is what we call as alternating currents, right? If you go back to the board, I will just brief this thing again. Simply what you have is two magnetic poles, right? A north pole is there and a south pole. So in between, we have the magnetic field lines. From north to south, we have magnetic field lines like this. So inside this thing, we have the coil. Right? Now these things are connected to the rings, right? I will show this one again in the video, right? So then the rings are connected to those two brushes. So then from the brushes we can connect this to any circuit, whatever the circuit we need, right? So then what will happen is when this one starts to rotate, right, on one side the current goes up, on the other side the current goes down. Okay, so that is because of the direction it cuts the field lines, right? So then on these sides, the horizontal sides, there will be no currents will be generated, right? So then whatever the current generated is taken out from these slip rings. Right, now if you go back to that video, right, right, so you can see, right? So then one side of this coil, let's say the side A, so side A connects only to this one ring, right? So it looks like the bottom ring, right? And the side D, the wire coming from the side D is connected to the other ring. So then what will happen is when the coil starts to rotate, right, you will see when the coil starts to rotate, right, so then these two rings also will be rotating along with it, right? Is it rotating? Okay, as you can see, when the coil is rotating, the two rings also starts to rotate, right? Can you see the rings will be rotating, right? So why do we need these rings, right? So that is because, you know, if we go back to the board, right, so if you just connect the ring to the circuit, right, so bulb or whatever the device we are connected to, right, what will happen when the coil starts to rotate, the wires get entangled, right? So they will be twisted and the circuit will be broken. So then to avoid that, we have to use these two rings. So then what will happen when the coil rotates, this ring is the one rotating along with it. So then whatever the brush is pressed up against it, the carbon brush or just the brushes, right, it's made out of carbon, right, so that one is pressed against this wire, right? So when the current is coming down from it, so then the current will go through this one and into the circuit. Same goes for the other part of the circuit as well. Okay, right, is it understood how the generator is working? Liliana? Okay, Tisha? Right, so this thing again slightly described in the note as well. In the generator, when the coil rotates, its wire cuts through the magnetic fields lines and a current is induced in it. So if actually it's again voltage is induced, and voltage is the one causing the current to induce, right? If we watch the just one side of the coil, we see that the wire moves up through the field and they are down for the each turn of the coil. As a result, the current induced in the coil flows first in one direction and then in the opposite direction. This kind of current is called the alternating current. A generator that provides alternating current is called an alternator. The size of the induced voltage can be increased by using much stronger magnets, so many more turns of the wire of the coil and spinning the coil much faster, right? So just like the one we discussed earlier, right? So we can increase the current in the coil in the whatever this generator by spinning faster or using a stronger magnet or making more turns in the coil, right? Right, so then to practice this one, since you haven't write anything, just write this as a question. I will tell you what are the points you have to focus on when you are writing an answer to this one, right? So I'll give you a few minutes to try this question first, so then I'll give you the correct, important points, right? You already know these things, right? So they are in the note as well, but write something. When you write things, it goes into the head. Yeah, I think that's enough. No? Time. Right. So what can we say? The first thing, explain how the current is produced in the generator, right? Now this is what you should write. Now the shortest answer, right? So you can mention, right, two sides of the coil. Now normally this will be given with the figure if it is coming. Two sides of the coil cuts the field lines when it rotates or as it rotates, right? So due to this rotation, right, so then what will happen? There will be a voltage induced in these sides, right? So then why it is when it is induced, the voltage is induced, what will happen? So then voltage is causing a current induced in the coil, right? So these are the keywords. Two sides of the coil cuts the field lines as it rotates. So then there will be a voltage induced as it cuts the field lines. So then what will happen? The voltage is causing the current. Okay. Next one, explain the purpose of the slip rings. So then why do we use the slip rings? They are used to take the current produced or the induced, or you can say take, or even you can mention supply the current induced in the coil to circuit, right? So this is just one purpose, right? So then why slip rings, right? And also it is used to avoid, right, the wires or external circuit wires twisting or entangling with each other as the coil rotates. Okay. So these are the reasons. Next one, mention 3 ways to increase the current in the generator. That one I also told you, right? So rotate faster, use stronger magnet, or use more turns. Right. I hope that one is clear. Right. So then you can move to the next part. Right. So next part is the transformer. Now this transformer is using the concept we were just discussing about the electromagnetic induction. Induction concept is used in the transformers, right? Now you must have seen this when you're going on the roads, right? So these things are there on the side of the roads, right? So in regular, like few kilometers at time to time, you have this, right? So inside this, right, so what is happening inside this is the what thing we are going to discuss here, right? So okay, I'll explain this with the board, right? Now the transformers are usually used to increase or decrease the voltage, right? Increase the voltage or decrease the voltage, right? So there are different designs are there to achieve one of these purposes, right? Normally what happens is whenever the electric current is generated at the power plant or the power station, right? So then what will happen now, say Norochole or Kotmale, wherever we have electrical power plant, right? So then whatever the electric power generated here, first we will increase the voltage using a transformer before transmitting into a different cities, right? You know, Noracholi is in Puttalam area, right? So if you want that currently has to be transferred to Colombo, right? So then before it transfers, right, we will increase the voltage, right? So why is this one is done, I will explain at the end of the lesson, right? Again, so then what will happen is, so then using one transformer it will be increased, so then it will be distributed from one town to another town, right? So then once it reach, now it will be increased. Now you have seen the extension wires like 66,000 volts, 33,000 volts, right? So even sometimes we have 132,000 volts, right? So I heard that in different countries we have even double of this value, 264,000 volts also used, right? In Sri Lanka we will see mostly 33,000 and 66,000 before transferring it into a distance towns, right? So that depends on how far it is sent across, right? So voltage will be increased, right? Now once it reaches the town where it needs to be distributed, so then again voltage has to be reduced. So then that voltage reduction is also done by another transformer, right? These are the ones we are seeing on the road. So the reduction, the voltage is reduction, those transformers we see on the roads, they are used to reduce the voltage. Okay, again then only we will receive, in normally in our houses we are receiving 230 volts. I think you may have learned about this, we may have discussed it in the second lesson, electricity lesson, right? So we are using 230 volts, or some countries use like 240, even some countries they are using 110 volts as well, right? So somewhere within this range, right? So this increasing and decreasing is done using a transformer, right? Let's see how the transformer is working. In a transformer, what you have is we have a iron core, right? Right, now this is iron core, right? So these part are empty, this is empty, right? It's not always this shape, right? Sometimes it can be this kind of shape as well, right? So then this part is the metal. Here also this is the metal part, right? So made using iron. Normally we know iron is a soft magnetic material, so that property is required. That is why we are using soft iron, called as soft iron core, right? So on the soft iron core we have two coils. We have two coils wounded around these two, and remember the number of turns in each coil will be different. In the one I drew, you can see in the first coil it has more number of less number of turns. In the second one we have higher number of turns, right? On this side, right, so we are supplying the current voltage, right? So we call it as input voltage. Can I use white? On this side we are supplying the input voltage. So the input voltage we are supplying is as an alternating voltage. Input alternating, that means change in direction, right? So normally that one we use the symbol like this for the alternating voltage supply. Okay, so this is input voltage, right? So then the output is taken out from the other coil. Right, so then now if you want to, now here let's say voltage has to be introduced, right? So then whatever the power supplied from generated from the power plant, it is connected to the input. So after the voltage has increased by the whatever this transformer, then the output is the one taking that increased voltage out, right? here this is what happens, right? Now we are supplying an alternating voltage, right? So alternating voltage has an alternating current, so that means the current is changing. Alternating voltage or the current means it is changing. So here what do we have? So here we have a coil with the current, right? So then we discussed in the previous last week, right? So then whenever there's current in a coil, there will be magnetic field. We even drew the magnetic field line structure as well, right? So whenever there's a current in this coil, there will be a magnetic field in this coil, right? And that day we have discussed, when the current is changing, the magnetic field also changing, right? If the current goes the opposite direction, the magnetic direction of the magnetic field is also changing. So then here, since we have supplied alternating voltage or alternating current, right? So then what will happen is the magnetic field generated in this this coil will be changing, and this coil is known as the primary coil, right? So this coil is known as primary coil. This is known as secondary coil. Primary coil and the secondary coil, right? So then what will happen? There's an alternative or voltage or the current is there in the primary that is changing. So when the alternating current is changing, what happens? There will be a changing magnetic field in the primary coil, right? So now what will happen? Now this coil is wrapped around a soft iron core, right? So because of this magnetic field, this iron core also become a magnet. Okay, so now the iron core is a magnet, and we discussed the soft iron has a change. I mean, it is the magnetism is not permanent, right? When this magnetic field gets stronger, then this magnet also become increasing. If this magnetic field in the coil gets weaker, the magnetism in the iron also getting weaker. If the magnetism, the poles of the magnetic field in this coil changes, then the poles of this iron core also changes, right? Now it is not just this part of the coil, right? So not only this part of the coil become magnet, this entire soft iron core become a magnet itself. So as a result, what will happen? So when this is a changing magnet, strength is changing, the direction, the poles, everything is changing in the soft iron core, right? So when that change is there, what will happen? That change is felt by this secondary coil, right? So if we summarize again, alternating voltage or the current in primary changes or changing, right? So this produce changing magnetic field in the primary, right? In the primary. So then what will happen? So change in magnetic field is felt by secondary coil, right? So how is it felt by the secondary coil? With the help of the that soft iron core, right? Even if that soft iron core is not there, we know when the magnetic field is changing, now they are not very further away, right? So they are very close to each other. So then when this magnetic field gets stronger and we can change in the direction, that change is felt by this secondary coil. The soft iron core is there to make it more make that field make that change in the field is felt by the secondary coil much better, right? Change in magnetic field is felt by the secondary coil. Now what will happen? Secondary coil is a conductor which is inside the changing magnetic field. Now we have discussed before, when there's a changing magnetic field with a current carrying with a conductor, right, what will happen is there will be a voltage induced this secondary coil, right? So then that is how we get in the voltage out of it, right? So now I will let you write this as a question, right? So don't write this because it's given in the note as well. secondary is in a changing magnetic field. So then what will happen? Voltage is induced. Right? So voltage will be induced in the secondary coil. So then that secondary voltage is what we taken out as the output voltage. So output voltage, so there will be a current. Yes, there will be a current, and there will be a voltage output as well. Right? Is it clear, Liliana? Draw this figure right next to your the transformer figure in your note, right? So somewhere here, right? So draw that same figure with the labels. So this one. So input voltage, the primary coil, secondary coil, soft iron core, and the output voltage. So we'll label these ones. So input voltage, we'll label it as V in, V1, or V out. This is V out. And one more thing, right? So we'll take the number of turns. That number of turns is important, right? When you're drawing this, draw with different number of turns. In the first one, in the primary, we'll take there are N1, Ni. Let's take both one as I and out. So this is V in Ni. VO. The number of turns in secondary is NO. Now we'll just use 1 and 2, this is V1, L1, V2, N2. Right, just draw this figure. Right, now I told you, right? So these transformers we can use to increase and decrease voltage, right? So that increasing or decreasing the voltage, that depends on the number of turns. That's why I said when you're drawing this, you have to draw with different number of turns, right? Normally there's a relationship. Actually, you have to mention this in this note as well. As an equation, right? So that equation is voltage supplied in the primary divided by voltage in the secondary is equal to number of turns in primary divided by number of turns in secondary. Or with the symbols we use, we can write as V1 over V2 is equal to N1 over N2, right? So you can memorize this either way. Okay, so write that equation there. Right, now here how it's happening, right? Now you can see V1 V1 or V2 equals N1 over N2, right? Now you can see if this value is high, the V1 will be high, right? So if V1 is high, that means V2 is small. Okay, so that means it will be reducing the output voltage, right? So if N1 is greater than N2, right? So then what will happen? V input will be greater than V output. So this kind of transformer, now you can say the voltage has been reduced. So they are known as step down transformers. Step down transformers, right? So then according to the equation, if the number of turns in the secondary coil is higher, so then the voltage will also be higher, right? It's like 100 and 200. So then what will happen? The voltage ratio is 1 to 2. So that means compared to V in, the output voltage will be double, right? So then N2 is greater than N1. So then what will happen? Voltage input is less than voltage output. So that means the voltage has been increased. So then this kind of transformers we call as step up transformers, right? And the voltage is increased. So simply stepped up means the voltage is increasing. The step down is voltage is decreasing, right? Now according to the figure I have drawn here, right, you can see the secondary coil has more turns, so that means it has more turns means it will produce higher voltage, right? So next to that equation somewhere, right, you just mentioned these two as well, right? So step up transformer and step down transformer here. Step up and step down. In step up, what will happen? N1 is less, N2 is great. So then what will happen? V input is less, V output is great. So the step down is the opposite. N1 is greater than N2. So then V input is greater than V output. So what is this? Step up and step down is mentioned here. It's the same thing is mentioned there. So if the secondary coil has more turns, then the step up transformer where output voltage is increased. If the secondary coil has less turns than the primary, it is a step down transformer where the output voltage is decreased. And so the working principle is also discussed here as well. A transformer is a device that helps to reduce or increase the voltage in a wire or electric line. This is made of two soft iron core linking to the coil at the two ends of the transformer. The first coil is called the primary coil and the second one is called the secondary coil. Well, alternating current is passing through the coil. The magnetic field around it continuously changing. The changing magnetic field will cut the secondary coil and the induced voltage in it. That's how the current is passed, right? So then that is the output voltage as well. So if then about this number of turns, right? And another important thing about these transformers is, right, so transformers are considered as 100% efficient, right? So 100% efficient means input power is equal to output power. Okay, so 100% efficient. Actually, in practical situation, it may be not exactly 100%, maybe 98% or something, right? But we are trying. Those who make those transformers, they are trying to keep it as much as possible, as 100%. At least closer to the 100%, right? So that means input power is equal to the output power. Now you have learned in electricity lesson the power is calculated using VI, right? So then input voltage, if we consider as V1 and input current, that means the current in the primary coil as V1 I1, so then this should be equal to V2 I2, right? In other words, we can write V primary times current primary equals V secondary times current secondary, right? So I either memorize V1 I1 V1 equals V I2 V2 or with primaries and secondaries, right? So this equation is about this equation is mentioned here. It is important to try to make the transformer as efficient as possible to keep any energy losses to a minimum. We use a thick copper wire for the coil and use a soft iron core covered in thin layer. That one is okay, right? So if a transformer is 100% efficient, then the electrical energy entering the primary coil is in each second is equal to the electrical energy leaving the secondary coil each second. So then we can write here, you can mention input power equals output power. So then we I I I1 V2 I2, right? Or else we can write V primary current primary equals V secondary current secondary. I1 is right. Mention this equation as well. Okay, so you can read this part, right? I'll explain. Now I told you, right, when it comes to the electrical power, I mean power station, right? So whatever the power generated in the power station or power plant, right? So then that voltage is sent through a step up transformer to increase the voltage, right? So then what will happen, it will be sent into distance down, right? So once it reached the necessary down, right, so we use step down transformer to reduce the voltage before it reaches our houses, right? Normally, in real situation, actually what will happen is this will be done in several times, right? Now when it's reached, let's say it's coming from Norochole to Colombo, right? So once it reached the Colombo, right, so voltage, let's say it's coming from 66,000, right? So first, from once as soon as it reached the Colombo, it may be reduced to 33,000 or something, right? So then once it reached the Colombo, right, so from the Colombo main electrical supply station, it will be distributed to different sections, right? Now maybe like Kaduvela, Avisavela, Maharagama, right? Dehivala, different regions are there around Colombo. For different parts, it will be sent through, right? So then this reduced one will be sent there, right? Let's say once it reached the Dehivala town, right? So normally in Dehivala, I'm not saying exactly in the hill, somewhere around there will be another small power station, right? So from there it will be once again reduced, right, to 11,000 or something, right? So then once again it will be reduced before we reach our house. It will be reduced to 230 again, right? So this reduction is happening in several times, right? Now why is this voltage increasing and decreasing is important is to save energy, right? Now according to this equation, you can see if the output, that means secondary voltage, is increased, now this value is the input power, no? So if the voltage is increased, the current will be decreased, right? Now if this value input power is, let's say, 1000 watts or something, so then output voltage also has to be 1000 to keep that value as 1000, right? What we need is when the voltage increases, the current will be reduced in the step up transformer, right? Now we know the electrical lesson you have learned, I squared into R is used to calculate how much electrical energy is used in, this is also used to calculate how much electrical energy is converted into thermal energy. So we know in those current wires, the wires we are using to say transfer the electricity from Colombo to Norachol to Colombo, whatever the transformation, those wires have their own resistance, right? So because of the resistance, what will happen is the wires gets heated, so then it will reduce the energy of those current, right? So then when the current is reduced like this, so then what will happen, so then actually current will be reduced to very small value, 0.00 values or something. So then according to this equation, when current is less, the resistance is still the same, so then it will reduce the energy loss. Okay, right. Okay, so this is the purpose of using the step up transformer. But when it reach our houses, we can't use 6,000 voltage, we need only 230, otherwise everything will be fried up. So therefore, to prevent that, to prevent that, we will be using this kind of technique, right? So actually this is what explained in the note. So national grids are networks of wires and cables that carry electrical energy from power stations to consumers such as factories and homes. Unfortunately, current in long wires can lose a lot of energy in the form of heat. So the larger the current, the greater the amount of energy loss, right? So if the current in the wire is kept to a minimum, so then the heat loss can also be reduced. Transformer helps us to do this. Transformers are used in national grid, so that national grid means the electrical supply in the country, so that the electricity is transmitted at a low currents and at high voltages. Immediately after generation, electrical currents from the alternators, that means the transformers, are passed through something like that. I mean, like converting into alternating current, it's mentioned before as well, which greatly decrease the size of the currents and increase the size of voltage. These step-up transformers increase the voltage of electricity to approximately 400 kilovolt, that means 400,000, right? So I don't know whether we are using that kind of voltage in Sri Lanka or not, but in some countries they may be. So then high voltages like this can be extremely dangerous, so the cables are supported at high above the ground on pylons. As the cables enter towns and cities, they are buried underground. Close to where the electrical energy is needed, the supply is passed through a step-down transformer that decreases the voltage to approximately 230, while at the same time increasing the current, right? So this is why we use the transformer generally, right? Is it understood the purpose and how we use the transformers and the working principle of the transformer? This will be asked in your exams as well, right? So especially in your second paper, transformers also is coming in the second paper. I will give you a small question, right? You can try that, and I will discuss that question maybe next week, because time will be running up, right? So write this question. You can try, and you can leave the meeting after you write in the question, and we'll be discussing this question the next time.